In this lecture we're going to talk about mass spectrometry, and I just thought I'd start it by standing in front of a picture of a mass spectrometer. The learning outcomes for this lecture are firstly to explain the theoretical basis of mass spectrometry, secondly to explain what is meant by the terms molecular ion and fragment ion, and thirdly to interpret mass spectra. Right, we're going to continue working on the experimental determination of structure. We've already covered elemental analysis, from which we get the empirical formula of the unknown sample. Next thing we can turn to is mass spectrometry to get a bit more information. So in this lecture I'm going to initially explain how you carry out mass spectrometry and look at the theory behind it. We'll then look at the spectra a mass spectrometer produces, and then we'll analyse the spectra. Okay, this is a schematic diagram for mass spectrometer. I would not expect you to have to reproduce this in an exam. If some of the writing is quite small, there's a copy of it in your lecture notes. There's four main steps in the mass spectrometry process. Firstly is vaporization, followed by fragmentation and ionization, followed by acceleration and deflection, and finishing with detection. So I'll go through each stage and talk about it in a wee bit more detail. So the first stage, the sample is vaporized just by heating it up till it turns into a gas, and it is then injected into the mass spectrometer. So the vaporization of the sample takes place externally, and the vaporized sample is injected into the mass spectrometer. The second step, probably the most interesting step, is the fragmentation and ionization. And all that takes place in this area here, the fragmentation and ionization. And this is brought about by an electron gun which fires high energy electrons at the vaporized sample. And what these high energy electrons do is they can fragment the molecule. So they can break some of the covalent bonds, not all of the covalent bonds, but some of the covalent bonds will get broken. For example, here's a model of butanol. Okay, so the ion gun, the electron gun firing high energy electrons might break that covalent bond, and you produce fragments of your molecule. Okay, so that's what we mean by fragmentation. Or it might break that covalent bond and produce those fragments. As well as producing fragments, it's very efficient at removing an electron from the fragments. So all the fragments have got a positive charge because they've lost an electron. So in the second step, the vaporized sample gets fragmented, and those fragments have electrons removed, so they have a single positive charge. Third step, acceleration and deflection. Well, at this end of the mass spectra here, we've got an electrically charged plate called a repeller, and it's got a positive charge. All the fragments produced in here have got a positive charge, so the repeller repels those fragments and fires them off down this tube. Okay. Halfway down the tube they meet a magnetic field, and magnetic fields deflects charged particles. So the charged particles get deflected round and eventually they hit an ion detector here which detects them. The clever bit is that the size of this deflection depends on the mass of the particle. If you've got a light fragment, it gets deflected a lot by the magnetic field. So I'm going to send a light fragment out of here and we'll see it get bent round by the magnetic field. So it gets bent a lot by a magnetic field, it gets deflected a lot, so it's quite a sharp curve, and it gets detected at the left hand side of the detector. A heavier particle which comes out, however, here it comes, gets deflected less, and it ends up being detected at this end of the detector. So by carefully calibrating this detector, you can actually get a measure of the mass of the fragment that's been deflected by a measure of how much it's been deflected. Okay, let's just run through all that one more time. So the first step is the sample gets vaporized, injected into the ionization chamber as a vapor. High energy electrons are fired at it, which fragments the molecule and removes an electron from the fragments. The positively charged fragments then get repelled down this tube where they meet this magnetic field which deflects them. The light particles that deflected a lot and get detected at one end of the ion detector. The heavy fragments only get deflected a little and are detected at this end of the detector. So that's the theory of mass spectrometry. You should have an idea. You should expect to be able to explain how mass spectrometry works. So let's have a look at the information that comes out of the ion detector. So this is what a mass spectra would look like. So along the bottom is it says M/Z, where M is the mass of the fragment and Z is the charge of the fragment. Now Z is in 99.9% of cases 1. So this is just a measure of the mass of the fragments. And up the side it's normally just a relative abundance, and differentiate peaks where there's an awful lot of fragments with that mass from smaller peaks where there's only very, very few fragments of that mass. We tend to concentrate on the major peaks. So something came out of the mass spectra with a mass of 136, 105, 77, 51, etc. And from that we can get very important information to help us identify the sample. So let's look at analysing the spectra. Okay. Right. The first thing to do is look at the highest peak. By that I mean the heaviest peak. So the peak with the highest M to Z ratio, because that represents the mass of the molecular ion. So some of the vapour that is put into the ionization chamber won't actually be fragmented. It will lose an electron, and then the parent ion, the molecular ion, in this case the butanol, so it just loses an electron, becomes positively charged butanol, and is fired down the mass spectra, the mass spectrometer. Okay, and that will be the biggest peak you see, the peak with the highest mass. So if you look at the highest mass peak, that tells you what the gram formula mass of the compound is. So if we look at this mass spectra, the peak with the highest M to Z ratio is 84. So that tells me the gram formula mass of the unknown is 84. Now if you combine that with the results of elemental analysis, which you already know the empirical formula, you can actually work out the molecular formula. So for example, if from elemental analysis you knew that the empirical formula was CH2, okay? But you didn't know if it's going to be C2H4, C3H6, C4H8, etc. But for mass spectra, you know the gram formula mass is 84, and so the molecular formula, in order to have a gram formula mass of 84, must be C6H12. That comes to a gram formula mass of 84 grams. So the empirical formula combined with the highest peak of the mass spectrometer can reveal the molecular formula, and that in itself is a very, very useful piece of information. All the peaks below the highest one are fragments of the molecule, and sometimes that can be very useful in trying to identify the exact structure of the molecule. Obviously C6H12 could have various structures. So there's some very common fragments that it's worth looking out for. Okay. So CH3, so I'll go back to my butane 2-ol here. See, a very common fragment would be a CH3. So that would have a M to Z ratio of 15. Another common fragment might be the carboxyl group in carboxylic acid, the COOH coming off, and that would have a M to Z ratio of 45, and so on and so on. So we're kind of looking for these common fragments. So let's maybe look at a question. Right, I'm going to show you the mass spectra of methyl benzoate. Perhaps will help you. I'll just draw out the structure of methyl benzoate. So okay, so there's methyl benzoate. Here's its mass spectra. And a typical question in an exam might be to identify the fragments that are responsible for these peaks. Okay. Well, the highest one, the 136, isn't actually a fragment, it's a molecular ion. Okay. And the way you would write it out would be, so it's C6, C7, so it's 8 carbons, so it's C8, 5 hydrogens, 1, 2, 3, 4, 5, plus 3, so C8, H8, O2, and then plus. Remember, all these species here are ions. Okay, so if you're asked to identify them, you need to put the positive charge in. So that's a molecular ion, not fragmented. These 3 other peaks will be fragments. Now the 15 is one that I pointed out in the previous slide. So the 15 would be brought about by breaking that bond there and just having your CH3 group. So the fragment responsible for the peak at 15 is CH3 positive. The 77 is quite a common one. The 77 is the phenyl group. So that would be if you broke that bond there, okay, leaving you your 6 carbons and 5 hydrogens. So the 77 would be caused by the C6H5 plus group. The 105, so that is 31 less than the parent ion, and we could get that by splitting the molecule here, okay, losing the 16, 28, 31. So that bit to the left would be responsible for the peak at 105. So that would be C7, H5, O plus. Okay. So a careful analysis of the spectra can allow you to identify lots of the peaks. Maybe not all the peaks, especially not the very small ones, but you can identify lots of the peaks, and that gives you some information about the structure. You know, from the empirical formula and this, you know the molecular formula, but you don't know what isomer of that molecular formula it is. The fragmentation pattern can assist in deciding what the structure is. So, finish off by showing you a past paper question on mass spectrometry. Oh, sorry, one more thing to say. Yeah, very occasionally you might get a question about a doubly charged species. Okay, so the mass spectrometer is very good at just producing a stream of singly charged fragments or molecular ions, but occasionally you can get some fragments that have got a charge of 2+, so in which case the M to Z ratio would not be an exact measure of the mass, because it's the mass is divided by 2. So for example, in cyclohexane, yeah, we've got the peak at 84 is the molecular ion, okay? But if you produce some of the molecular ion with a charge of 2+, the M to Z ratio would be 42. So some of this, the smaller peak here at 42 could be due to the molecular ion with a charge of 2+. I just mention that for completeness. It doesn't very often come up in the questions, but you never know. So 99.9% of the information here, the charge is just 1+, so it's just a measure of the mass. But occasionally you can get doubly charged species. But don't have that in the forefront of your head. Most of these things will be singly charged species. So here's a past paper question. Part of the mass spectrum of propane-1-ol is shown below. So the three questions are, firstly, in the mass spectrometer, what causes the ionization and fragmentation of the propane-1-ol molecules? So the stresses, it's important to know the process. B, draw a structural formula for the ion fragment which gives rise to the peak with the mass to charge ratio of 31. And finally, which has nothing to do with mass spectrometry, draw a structural formula for the compound which is isomeric with propane-1-ol but belongs to a different homologous series. So pause the tape, come up with answers to those questions, then we'll go over it in a minute. So question A, in the mass spectrometer, what causes the ionization and fragmentation of the propan-1-ol molecules? So an acceptable answer to that would be the electron gun or the high energy electrons. B, draw a structural formula for the ion fragment which gives rise to the peak with the mass to charge ratio of 31. So let's draw out the propan-1-ol molecule. And try and work out what fragment is responsible for the peak at 31. Well, if you broke the molecule there, this fragment here comes to 31. Now, if the question had just said identify the fragment, identify the ion fragment, you could write your answer as CH3O+. But in this question it says draw a structural formula for the ion fragment. So in that case, because I want a structural formula, we would need to draw it as that. So that's the structural formula for the ion fragment at 31. And finally, not so much about mass spectrometry, but draw a structural formula for the compound which is isomeric with propan-1-ol but belongs to a different homologous series. Well, the idea is you should remember that alcohols and ethers are always isomers of each other. So if we draw a structural formula for the ether with 3 carbons, So 2 carbons on one side of the oxygen, 1 carbon on the other side of the oxygen. So both the propanol and the ether have got 3 carbons, 8 hydrogens and 1 oxygen. The learning outcomes for this lecture were firstly to explain the theoretical basis of mass spectrometry, secondly to explain what is meant by the terms molecular ion and fragment ion, and thirdly to interpret mass spectra.